Hey everybody, welcome back to Calculus. So surprisingly, we've already gotten all the way through Unit 5, and there's a couple more things at the end of the chapter about probability and things like that. If you're going to go on, take a stats class someday, which a lot of you will, that would be something that would come up in it. They have probability density functions and all this other kind of stuff, and it might be worth just skimming over and trying to get a gist of it, but there's nothing formal over the rest of the chapter. So we are done with everything that you'll be tested over for chapter 5 of this applications of the integral. And we're going to start reviewing today. It shouldn't take too long. We're going to give a quick, brief overview of everything we talked about in this unit. And of course, most of the time studying, you'll be working on review assignments. There are 2 of them, and work on those at your convenience. That's essentially what your job is for this entire week, is to work on your review assignments, get them taken care of, and then over the weekend, you'll have your last test of the year. It'll be a take-home test, and you can work at that at your leisure, get that all off your plate, turned in, and then your grades will pretty much be set where they're going to be. There will be some more homework. We're going to dabble in some other units about more about infinite series and Taylor series and polar coordinates and some what else is there? Differential equations. We're going to talk about that. So we will touch on other ideas that you would go more in depth on, perhaps in a more rigid calc class in calc 2, maybe calc 3 kind of things. But essentially, we're going to just be done with the main material for the course now and dabble in some other minor things that would be gone into in more detail in future classes. So you do want to kind of understand the gist of them. As long as you do your homework and finish up strong, you'll be just fine for the course. So let's start our review after we warm up, of course. Warm up today. A full ice cream cone is 3 centimeters long and has a radius on the top of 1 centimeter. If the density of ice cream is 0.025 kilograms per cubic centimeter, how much work is done if you slurp the ice cream out of the cone? So essentially, problem here is like one of those swimming pool problems or something like that. How much work is done to lift something up? Every slice of this cone at that level, it'll take a different amount of work to take that slice and lift it up because they have all the slices go different heights to the top of the cone. So we're going to figure that out. Now, one thing before we get into number 1, before I want you to notice this, is everything is given in funky units, centimeters. You don't want centimeters for squat, okay? You do want kilograms, that's good. But you never want things to be in centimeters. You always want to convert it over to meters. So before I even get into that one in a minute, 3 centimeters, you would call it 0.03 meters. 1 centimeter, you call 0.01 meters. And the density, you have to convert the cubic centimeters to just cubic meters. That would end up having to multiply that thing by 10 to the 6th power, like 0.025. So it's like 25,000 kilograms per cubic meter. So convert things over to standard units first, okay? There might be a way around doing that. You could use the units they gave you, but it's going to be very confusing. It's very easy to jack things up because everything's metric with kilograms and just meters and just seconds. So if there's anything not in those units, the first thing you want to do in any problem is convert them over. And that's the first thing we'll do in that. Number 2, you got a horizontal force applied to an object. It's given the mass and the force. Newton's second law, you can do F equals ma to figure out the acceleration. And then you can just do some basic kinematics, or if you know the acceleration, you can integrate it up to velocity, you can integrate it up to position. And that's kind of what you're going to do on number 2, because it asks you how far it went, what its final position is. Number 3, just a good old practice of taking a function and spinning it around an axis somehow. Find the volume of that function revolved around the x-axis from x equals 0 to 2. Depending on what the situation is, we might want to choose shells, we might want to choose discs and washers. Depends on what's going on. On your test, I might specifically say do this by discs. I might specifically say do this by washers. Or I might just say choose. You get to do whatever, which way you want. So we're going to solve all those and then quick review, and that'll be the lesson for the day. All right, number 1. Now, you may recall the key to any cone problem is similar triangles. So first thing you want to do is, if you know the entire cone is 3 centimeters high and 1 centimeter in radius, then whatever level the ice cream is at, okay, so let's just say you're down here. In fact, let's just make this the y-axis up and down, because up and down is usually y. You could use x, doesn't really matter, okay? But if you're at some random y value down here, well, there's a similar triangle with a radius r and a height, I guess we're going to call it y. So let's say down here at the bottom is where y is 0, just to make it easy. And then whatever level you're at is just whatever y is. So y is going to go from 0 all the way to the bottom, all the way to the top, because it's all filled up of 3 centimeters. But this little slice we're looking at, and that's what you're going to do. Cut the little slice because every single level has to be brought up at a different height, different amount of work on it. We're just going to look at a slice at a time. This particular slice, though, if you look at the similar triangles, R is to Y as 1 is to 3. So R over Y is 1/3, and solving for R, that would mean the radius at that spot will be 1/3 of whatever Y is. Okay. Now, for just this little slice, not this part filled in down here. I don't care about that. I'm just talking about this slice right here at this height Y. If you took a cross section of it, what would be that volume of that cross section? Well, if you took a cross section and looked at it, it'd be a circle with a thickness of dy. So the volume of this little chunk of volume, dv, is the area of that circle, okay, times the thickness of it, which is dy. Well, the area of a circle is pi r squared. So dv is pi r squared dy. What's r, though? You want everything in terms of y. It's dy stuff, right? Automatically. So you have to put everything in terms of y. Well, what was r? R was 1/3 y, which when you plug it in for r and square it, you get 1/9 y squared. Putting them all together, dv would be pi over 9 y squared dy, okay? So there's the equation for a little bit of volume right there. You cut the slice, okay? Got yourself a cross-section of a circle, thickness dy. There's the equation specific to this cone of what dv would be, pi over 9 y squared dy. Okay, now we're a long way off from work, though, okay? Work is force through a distance. So forces are about gravity in this case. Gravity is what's pulling it down, okay? So I'm going to need to find the weight of this slice. But before you find weight, you got to find mass. So how do you find the mass of this little sliver you just did? Well, mass is just, if you know the volume of this thing, it's just the density volume, mass per volume, times whatever volume you got. So a little piece of mass is rho v, that's your volume density, that's the kilograms per cubic meter. We did convert it. It's not 0.025. Per cubic meter is 25,000. Okay, so everything's in meters right now. That's good. Times dv. Well, okay, so rho is 25,000, dv is pi over 9 y squared dy. You put it all together with a little bit of, you know, just turn it to a decimal just so it's easier. That's all lumped together as 8,726.65 y squared dy. Okay, now we got mass. We know the mass of the slice. How do you get the weight of this little slice? Well, weight's a force, okay? So you could say dw, you could say dm. I'm going to say dw, so you could say df. I'm going to say df, okay? It's a force. So at the bottom level, this is a force. So df. Well, how do you find the force? It's the weight, okay? Weight is just mass times the acceleration due to gravity, little g. In our case, a little bit of force, a little bit of weight of the slice, df, is just a little bit of mass times g, okay? So g is our good friend 9.81, or in the textbook, 9.8. Meters per second squared, everything's metric, so you want to use the metric one. So g times the dm would, in the end, turn out to be 85,608.4 y squared dy. Okay. All right, so we got the weight of this thing, the force that gravity's pulling this little slice down, df, finally. Now, let's talk about how much work it takes to take that force, that weight, and move it all the way the distance to the top of the cone. Okay, now in this equation, dw, a little bit of work, is x df. X is not literally x. X stands for the distance that this thing is moving. It moved a distance x. This little force df got moved a distance x. That's what the work is. Okay, now for us, how high am I raising up this slice up to the top of the cone? That's the point, right? Well, the top of the cone y value is at 3 centimeters, but we want meters, so 0.03, okay? Minus the bottom y, which is just a y value. We just have some random slice where y is y. So that height would be 0.03 minus y. So the x in my equation, which represents the distance you pulled it up, is just 0.03 minus y. So finally, we got our equation for an infinitely small little bit of work for this slice. This slice, dw, the work is 0.03 minus y, that quantity, times the df, which was 85,608.4 y squared dy. All right, so finally, after all that thought process, we're to the point where we know what the work is done for a little slice. All we got to do is add up all the slices now from the bottom to the top, because the whole thing's filled up, correct? So what's the bottom y value? It's the bottom of the cone, and we set that up to be 0. The top of the cone is 3 centimeters up, but not centimeters. We want meters, 0.03. Okay. So you plug all that in, you slap an integral on this thing. The 85,608.4 is a constant. You can bring that in front. So you're integrating from the bottom of the cone, where y is 0, up to the top of the cone, where y is 0.03, times the dw, which is this quantity right here. And if you went and did that and carried out the calculus, you'd get 0.00052. Okay, so what's our unit for work or energy or any of that stuff? In metric system, it's joules. So the work that would be required to do this is just not very much, 0.00052 joules. And that'd be my answer for that one. Okay, tricky problem. It doesn't get any worse than that. It's got geometry in it. You have to think it through every step of the way. If I took this slice, what's the volume? If I took the volume times the density, I get the mass. If I take the mass times g, I get the weight. And then the weight is a force, and how far did I go up? So it's got a lot of working components on this. These are the good ones to study because it doesn't get any worse than this as far as putting things together. Okay, and number 2, you had a force applied to an object with a mass of 5 kilograms. You want masses in kilograms. Cool. Kilos, that's the one thing you want kilos in. Okay, when a metric prefix is grams. But you do want kilograms. So mass is 5. And they gave you the force as a function of time. So somebody's pushing on this thing faster and faster and faster. The force applied starts off at 0. It just goes up quadratically. So it's going really fast. And it started at rest, if you read the setup. So the velocity at time 0 is 0. That's no speed at the time 0. It doesn't matter what you call your starting position, because the point is to see how far it went. So by convention, usually you just call x of 0 equal to 0. And the question was, how far does this thing move after 1 second? So you're looking for the x coordinate after 1 second. This is the big question, x of 1. Okay, well, how do you start off with these problems? If they ever give you a force and they ever give you a mass, Newton's second law of F equals ma should pop in your mind. So it does. F equals ma. Plugging things in, the force was 50t squared. The mass was 5. The acceleration I don't know, but I can solve for that now. Divided by 5, the acceleration is 10t squared. So that's what section 5.5 was all about. It's just like essentially the relationship between acceleration, velocity, and position going up the chain. So if your acceleration is 10t squared, what is acceleration? It's the derivative of velocity. So dv over dt is 10t squared. You can multiply both sides by dt, slap an integral on this thing. 2 ways to go about this. You could do as an indefinite integral and put a constant on the end plus c, and then use your initial conditions up here to figure out what the constant is. Or you can use a definite integral, and t is the easy one. It always goes from just 0 to t. So I'm just starting at time 0, and I'm going to some random time t. Okay. If you do that, and I recommend you try to do that, it's a little bit more mature. But if you do that, then the limits on the other side have to reflect that. Okay. So if the limit on the right was about t being 0, then the left, since you're integrating velocity, the velocity would start at whatever velocity it is at time 0. And if your limit on the right went to just some random time t, then the integral on the left with respect to v would be going up to the velocity at time t. So either way, it doesn't matter how you do it, but I like to go this way. So if you integrate the left dv, you just get v. Plug in the top limit minus the bottom limit would turn into v of t minus v of 0. On the right, you integrate 10t squared from 0 to t, that would have turned into 5t squared when you're done. And since v of 0 was 0, the starting velocity was 0, that just means that in the end, our equation for velocity at any moment in time is just 5t squared. Okay. Well, then you do the same process again. If you had acceleration and you were able to get up to velocity, now you got velocity and you're going to go up to position. What is velocity? It's the derivative position with respect to t. So dx over dt is 5t squared. Again, multiplying through by dt, you get dx is 5t squared. Slap some integrals on that. Exact same kind of logic on that. If it goes from 0 to t on the right, because it's with respect to t, on the left, since it's with respect to x, it's going to go from x at time 0 up to x at time t. Okay. Integral of dx is just x. Plug in your top limit minus your bottom limit would give you x of t minus x of 0. Over on the right, integrating 5t squared would give you 5/3 t cubed, which when you plug in the top limit of t minus the bottom limit of 0, you would get 5/3 t cubed. And since you chose to call your starting position x of 0, 0, and plugging that in, that just means that x at any moment in time is 5/3 t squared. Well, you're just trying to find out what x is at time 1. So plugging in 1, that would mean that x is 5/3. And all this was in kilograms and newtons. It's metric. So this is a position. It does have units. The units in metric would be meters. So the final answer would be 5/3 meters. And lastly, this one, we're just taking basically the function y equals x squared, and we're going to revolve it around the x-axis between the lines x equals 0 and x equals 2. So this is back to disks and washers and shells and things like that. I think in this problem, you could go either way. You could do shells, you could do disks. You would not need to do washers, because if you look at the region in gray right here, there is no gap between the gray and the axis of rotation. There's nothing you need to take out. So washers would certainly not be appropriate on this one. I went with disks. So as a refresher, what's the concept for disk? Well, you're taking a little slice, right? Your slice is perpendicular to your axis of rotation for disks. And that slice, you're spinning all the way around the entire slice, making a circle with area pi r squared. The thickness in this case would be dx thick, and that gives you a little chunk of volume. So yes, if you took this strip somewhere randomly in my region, we're spinning it around this axis right here where it's the x-axis. This strip, you spin around, well, it's got a certain height, which would be the radius of the circle that I create. So it's going to create an area of pi r squared. Thickness is dx. The area times the thickness would be this little chunk of volume. Okay, well, what is the radius? Well, it's just the height of this stupid strip. The strip goes from the top y value, which is the y value, there's just the y value of this blue curve, which is x squared, minus the y value down at the axis of rotation, which is 0. So top y minus bottom y would just be x squared. So your radius is x squared, but don't forget that x squared, the radius, needs to also be squared. So in the end, the equation for this specific function to revolve around the x-axis for a little chunk of volume, this little slice, is going to be that dv is pi times x to the 4th dx. And that's pretty straightforward from there. Now that you got your equation for dv, slap an integral on this thing. X goes from 0 to 2. And if you integrate that properly, you should get 32 pi over 5. So this is a straight math problem, no units, so no units in the answer. It's units cubed if you want to write that, but that's kind of stupid, so you don't need to worry about that. 32 pi over 5. So there's kind of a round robin of various things, mostly from the last section with applications, but also starting to refresh on disks washers. So learning goals today: begin to review chapter 5 in preparation for the test. Here are 2 review assignments. Take a second and write these down. There's one that's right out of the book, okay? It's homework 5.7, various problems from them. They'll be a little challenging and stuff like that. I'm also going to have just a worksheet one when I created homework 5.8. Those will be due later in the week. The first one, the book one, I'd like you to have wrapped up by Thursday. The one I assign you, work on that at the same time throughout the week, and that one's due on Friday. And you should have those both turned in by Thursday and Friday and off your plate for the weekend, because by the weekend on Friday or so, I will, maybe even earlier Thursday, I don't know, but sometime late in the week, I will post the actual exam. Your job is to download it and do it just like a homework assignment. Take as long as you want on it. Use any equations you have. That's essentially it. I mean, just do your review assignment. Hopefully you're refresh on all the methods we have and be okay on it. The worst ones are going to be the physics applications ones. I will try to make them too difficult, but try to get the overarching concept behind all these things. Okay, this is what an impulse is. This is what work is. This is how I take a mass and turn it into a weight. And this is how I take a density times something equals a mass. And try to get the general ideas down, because if you can understand that, the ones on the problem won't be too complicated, or on the test won't be too complicated. And hopefully, if you understand the simple ideas, you can put them together in the right way to actually solve the problem. I'm not trying to kill you on this thing, but I am trying to test that you know the basics of all those physical applications. All right, here we go with our review. Let's do this. Okay, so first things first. This was chapter 5, applications of the definite integral. Section 5.1 started off slow, okay? It was just about the area between 2 curves. I really tried to hit hard that for this, you're setting up little tiny strips between, like, say, a top function and a bottom function, and how do you set up the area of that little strip? The area is just the height times the thickness, right? The height is the y on the top in this picture minus the y on the bottom in this picture. So top y minus bottom y would be the height. The thickness would be, in this case, dx, thick. So that would be an equation for a little chunk of area dA. dA would be the y on the top minus the y on the bottom times the thickness dx for this picture. Of course, you could go the other way. The one on the bottom, on the very bottom on the right, is more dy thick, okay? It's the same concept. It's still a rectangle. How do you find the area of a rectangle? Length times width, or height times width, whatever you call it. The height is dy. The length in this case would be the x on the right minus the x on the left. Make sure you always do the most positive one minus the most negative one. So that's why it's right minus left. In that case, yeah, dA is just the x on the right minus the x on the left times the height, which is dy. Same concept there. This one's really good for when you can write everything in terms of y's. You can write, x in terms of y, and the other x on the other curve in terms of y. The first one is more good when you can write all the y's in terms of x's. So it depends on what you're doing, but essentially that's it. The only hard part is you might need to figure out the limits of integration. If two curves intersect, you'll have to do some algebra to figure out where they intersect. So in this middle picture right here, looks like they're doing dx stuff. So the first thing they do algebraically is set these two equal to each other. They would figure out where they intersect, and they would be at x equals -4 and x equals 3. And that tells you that, okay, well, the limits are going to be from -4 to 3 for x's. Okay. If you're doing this one down the bottom right, though, that's dy stuff. It's dy thin. So you'd be going from whatever the y value starts down at the bottom to the y value on the top, which would be from, I guess, 0 to 1 in this picture right there. Okay, so let's start off nice and slow, but you can see throughout the rest of the unit that you keep using strips for various things. You spin them around an axis, you set them up, spin them around this way for shells, all kinds of stuff, especially even when in the applications section, you take a little strip of something and you gotta go. So knowing how to set these strips is very, very important on a basic level because it filters through all the rest of the unit. This one looked relatively simple when you first did it. You had no idea what was coming, but it was all based on this idea of strips. So that's a review of the strips. 5.2 was about slicing discs and washers. Now, the idea of slicing was really, really easy. If I could just take a slice of something and figure out what the area is of that cross section, and I know what the thickness is, probably dx or something like that. I guess dy is according to this. If I took it, it doesn't matter what you do. But if you got an area times a thickness, that gives you a little tiny chunk of volume. Okay. Now on the test and the review assignment, if I was to give you one by slicing, I'd flat out say, okay, here's the area as a function of x. A of x is x squared minus 3 or something like that. And if I give you the area time as a function of x, you just multiply by dx. That gives you your dv. Slap an integral on it from x start to x end, and you're done. And vice versa. You could go the other way, of course. You could take a slice of this way, and its thickness is dy. And if you could figure out the area is as a function of y, times those two together, that would give you a little chunk of volume. Integrate them all up from the y bottom to the y top, and then you're done with that too. Okay, so slicing, it's not going to be complicated. We're digging into some esoteric things about like pyramids and coming to a tip and all this other fancy stuff, and the book has lots of complicated things as well. But on the test, you won't be anything that complicated. I'll just flat out tell you, here's an equation for area, and all you got to know is, okay, I either multiply by dx or dy, and then I integrate it. That's it. Okay. Now, the ones that are less obvious are the discs and washers. That was also from section 5.2. That was the concept that if you take a strip, okay, a nice little rectangle up and down, let's say, and I rotate around any axis that is perpendicular to it, spin it around. Then, when you spin it around that axis, the entire strip is being spun, not just the top, not the whole strip. When it does, it would make a filled-in circle as it spun around, and that circle would have an area of pi r squared, okay? Times the thickness, which is either dx, if it was going around this way, then dx, if it was a circle going around this way, be dy thick. But if you multiply those two together, pi r squared times the thickness, you get a little chunk of volume. And then again, you can integrate it from wherever you start to wherever you end, if x's or y's or whatever you're doing, that's fine. If, though, your region you're integrating around some axis has a gap in between it, then you have to use washers. And washers is the same exact idea. You're just going to find the area, the volume, if you rotate all the way, including the gap, to the top of your region, way at the top on the outside, okay? If you rotate all that around, it's too much. You got to subtract off this gap that you did spin around. So your inside radius that you subtract off would be from the axis to the start of your region right there. So there's an r outer, that's the distance from your axis to the end of your region. Okay? So right there to there. Okay? And there's an inner radius, which is from your axis of rotation to the gap. So it'd be from right here down to the gap. Okay? They might call it r outer and r inner. It might use a big R for the outside, big radius, the outside one, and a little r for the inside one. That's what I do. It doesn't really matter what you do, but that's the concept. And if you set that up carefully, again, this could go either way. You could have dx stuff, that your slices could be going up and down. You spin them around this way, that's times dx, or your slicer could be going this way around an axis that's perpendicular to it up and down, like an x equals something. And when it spins around this way, it makes a circle, and the thickness is dy. So it just depends on what situation works better. Whatever they're given to you, if x is a function of y, clearly you'd probably want to do dy stuff and all that stuff. But you're really forced, if you're doing discs or washers, to choose which one you're doing based on the axis. So if you're revolving around a horizontal line, it's got to be perpendicular. So you're going to do up and down strips with thickness dx. If you're going around a vertical line, then your strips are going to be like this, spinning around, and that would force it to be dy kind of thing. So that's discs and washers. Take out your gaps if you need to. Okay, that was section 5.2. 5.3 was another method of finding volumes by taking functions and spinning them around axis, but it was totally different. This one was by using shells. So in this one, if you have an axis of rotation, your strips are parallel to it this time, okay? And when you don't spin around the inside from here to your strip, you just take the strip, and only the strip, and spin it around. When you do, it'll go all the way around your axis, and the distance it went around is the circumference of a circle, which is 2 pi r, okay? R would be the distance from your axis of rotation to your function, to your strip, okay? So same always logic to figure out what R is in that, maybe x right minus x left, or y top minus y bottom, or whatever, that's your R, okay? The H stands for the height of the strip, so how long it is, essentially. If it's going this way, H stands for this length. If it's going this way, H stands for this length, but it's the length of the strip, essentially, okay? Because you're going to take this thing or spin it around. It's 2 pi r all the way around. How high this little shell will be the height of your strip H. So 2 pi r times H will give you the area of this shell, but this shell has some thickness too. If you took your strips this high, for example, well, your strips are dx wide. So you need to multiply by that to get up to a volume, and that's the concept there. 2 pi r to get one of the dimensions, H to get the second dimension, thickness to get the third. Because this is a three-dimensional thing, it should be a volume. And of course, vice versa, if you went the other way. Let's say you were going around this axis right here. Again, your strips need to be parallel in this case, all right? So in this case, if this is the strip I'm spinning around this distance would be r, right? Distance from the axis. The height would be the length of the strip. It'd be this little length right here, how long that thing is. That's what your height is in this case, okay? And the thickness would be dy in this case, and you'd spin it around. And the idea is kind of like a Russian thing, you know, like I can find the volume of this little shell, and the volume of this shell, and the volume of this shell, add them all up, like those Russian dolls, then it all adds up to the total volume in the end right there. And that's cylindrical shells, okay? So keep those straight, all right? The discs and washers, your strips are perpendicular to your axis of rotation. Shells, your strips are parallel to your axis of rotation. So hopefully after some review of problems, that'll come back to you a little bit. It won't be that bad. Section 5.4 was a nice break for you. It's about arc length and surface area. Okay, now arc length directly comes from Pythagorean theorem. So if you zoom in and zoom in and zoom in and zoom in on a curve, it essentially looks like a nice little line. ds would be the length of that little line, and it makes a little right triangle. Dx squared plus dy squared equals ds squared, little s. Okay, little s is for arc length. And that means that if you solve for ds, ds is the square root of dx squared plus dy squared. Okay, now that is what I always wanted to harp on. This is the big idea, and you could generalize this to 3 dimensions. So like ds would be the square root of dx squared plus dy squared plus dz squared. So this is by far what you want to know, especially if you're going like polar and things like that someday. You know, you want to know what you can figure out what dx is, you can figure out dy is, it's parametrics, it's things we don't have time to get into, but you could do that. So this is by far the thing you should understand. But as far as practical applications for you guys, if your function y is a function of x, you want to integrate with respect to x. If you factored out a dx squared from under the root, the square root of it would be dx, you'd be left with this little expression right here. ds is the square root of 1 plus the quantity, dy over dx, the derivative of your function with respect to x, that is squared, times dx, okay? On the other hand, if they give you x as a function of y, you'd want to integrate with respect to y. So if that case came out, then you wouldn't want to factor a dx squared out of this, you'd want to factor a dy squared out. And similarly, if you took a dy squared out, square root of dy squared is dy, you'd be left with the square root of 1 plus the x over dy quantity squared, and you got x as a function of y, so you can figure out what dx, so take the derivative both sides with respect to y, you can get dx over dy and plug them in. Very straightforward to plug those in, okay? So arc length isn't that bad. And remember this, if you're just going along a curve, this just represents a little tiny piece of it, just a little bit of length of it right there. Okay. Now, if you had an axis of rotation and you took this little arc length and you spun it around, just that little piece, I'm not talking about a strip, I'm not talking about the inside, just that little tiny piece of arc length, then that had a certain length, ds, it got spun around a distance all the way around on a circle, which is 2 pi r. So the surface area created by that, there's a two-dimensional thing, a ds times a distance around. That would give you d big S, and big S stands for surface area, okay? If you wanted to write dA, I guess you could, but you need to get more mature with that because eventually in mathematics I start using big S for surface area and not A or anything like that. But that's a separate thing. So again, ds, the area you swept out, is 2 pi r, and r is of course the distance from your function down to your axis of rotation, okay? That distance, 2 pi r all the way around, this thickness was ds, so the equation for surface area of d big S is 2 pi r d little s. So it's pretty straightforward. You just kind of set up a radius again, kind of like you do with distance and washers to figure out what that is. ds is from the arc length, which we just kind of talked about, so it builds on arc length. You put it all together, slap an integral on this thing. And of course, if you're doing with respect to x dx, you go from x to x. And if you're doing from y, dy stuff, then it's from y, bottom to y top kind of things. And it's pretty straightforward from there. Section 5.5 is about projectile motion. That is essentially boils down to these a couple kinematic equations. You don't need the jerk one. You don't need that also. You should know by now that if you take position x, I'll say x, doesn't matter what letter you use, it could be y. In fact, this works in any dimension possible. Calc books might use a little s for, position or something like that. It's weird. But if you know the position x, say where something is, and you take the derivative of it with respect to time, that is velocity. How quickly my position changes with time, miles per hour or something like that, meters per second. So velocity is the derivative of position with respect to time. Got position, take the derivative with respect to time, you get down to velocity. If you got velocity and you take the derivative of that with respect to time, you get down to how velocity is changing with time, better known as acceleration. So these two differential little equations right here, v is dx over dt and a is dv over dt, those are your babies, okay? It will get you through anything that has to do with projectile motion or motion in general. Even if your acceleration is not constant, it'll still work out for you. Most of these, they're going to apply these, though, to gravity problems, okay? With gravity problems, number one, let's talk about how you would set those up. There is going to be, for all three of these concepts, you need to think about their initial conditions. But there are two different kinds of coordinates going on for most gravity problems. Something's going on the x and something's going on the y. So the first thing you do, if they give you a problem that involves both x's and y's, something's launched at an angle or something like that, the first thing you do is you break it into components, okay? So say something's chucked at a starting velocity v naught, and that's this hypotenuse at a certain angle theta, okay? You would use basic trig, all right, sines and cosines, to figure out, based on that angle and based on the length of the hypotenuse, which is so many meters per second or something like that, you would be able to figure out this side, this length right here. Now that would be the x side. So that would tell you the starting velocity in the x direction, okay? If you use sine, then you would get the other side, which is the up and down one right here. And that would be, well, how much the starting velocity is in the y direction. Now, once you have that figured out, your x's and y worlds should completely separate, okay? You're going to do everything with x's separately and everything with y's separately. It's two problems in one, okay? Now, here's the deal. Let's think about this through. Every one of these things has positions, velocities, and accelerations. So you need to know all their initial conditions, okay? let's go with x's and y's, okay? Starting position. I need to talk about x and y. They're separate problems, but I need to know both. Typically, if you're launching something like this from the ground right here, you would probably call the starting x position x of 0, 0. And separately, in your y stuff, you'd call y of 0 equal to 0. Okay, so name something convenient if you can. Now, if they start off with something raised up 50 meters and then shot off or something, well, x of 0 you could still call 0 because the x coordinate's still 0, but your y of 0 would be probably 50 or something like that. Convenient to make y equals 0 be the ground. That's a very common thing we're going to have to do right there. But we're going to treat these separately. You know what the x starting is? You know what the y starting is? Check. Do you know what the starting velocity, v of 0, is in the x direction? Yes, you do. You just found it by breaking up this triangle. It's the length of this red line right here. Do you know what the starting velocity is at time 0 for the y direction? Yes, you do. It's the up and down red line in this picture right here. So you know your starting positions, x is 0 and y is 0. You know your starting velocities, the velocity in the x direction at time 0, the velocity in the y direction at time 0. What about one more layer deep? Acceleration. Well, horizontally with x's, gravity is the only thing working on this thing. That pulls up and down along the y's. There is nothing going on along the x's. So the acceleration in the x direction is a big fat 0. So if you're going down your x side, acceleration in the x direction is 0. That's cool. On the other hand, gravity does pull things up and down in the y direction. So if you're doing the y direction, your acceleration should be, first of all, it should be negative because you're going to assume up is positive and down is negative, and gravity drags things down negative. What number should you use for the acceleration? It is a constant. If you're doing meters and metric stuff, the number to use is 9.81 meters per second squared. I'll take 9.8 since the book uses 9.8. Or if they're doing English system, it'd be 32.2 feet per second squared, but the book uses 32. Okay, so you know everything about the start of this problem. Okay, you know x is 0, you know y is 0. You know the velocity in the x direction times 0. You know the velocity in the y direction times 0. You know the acceleration of the x in the x direction is 0. You know the acceleration in the y direction is negative 9.81 or negative 32.2. You know everything about the initial conditions. What do you do then? Well, you go down the x chain, okay, and you go down the y chain, and in either case, you're doing the same thing. In fact, you're going to work them probably from bottom up on this. So if you look at the x's, start the acceleration in the x direction, which is 0. Acceleration is dv over dt. You move things around, you integrate, you solve for the velocity, which would be a constant because its derivative was 0, acceleration was 0. So the velocity in the x direction will be a constant. And if you plug in your initial conditions or integrate with a definite integral with your limits correctly, then you should have an equation with this without any constants. Then you go up the chain again. If I know my velocity in the x direction is, I can integrate that and just get x in general. What is the x position as a function of time? Again, plug in your initial conditions and there should be no arbitrary constant. And you can figure out everything about x's. Separately, you go do that with y's. The acceleration in the y direction starts off being negative 9.81. Well, that's the derivative of velocity with respect to time. So you integrate that thing. And then you get the velocity in the y direction as a function of time. Okay, well, now I got that. Integrate that with respect to t. Boom, now I got y as a function of time. So you should be, in the end, getting equation for x of t, y of t, the velocity in the x direction, the velocity in the y direction, and the acceleration in the x direction and the acceleration in the y direction. You know everything about all three of these things, position, velocity, and acceleration in both dimensions, x and y, separately. Okay? Then you can use that to solve various problems. Key things I might ask you to solve for in this is, when does it reach its maximum height? The main thing you need about this is, when it reaches the maximum height, it doesn't stop moving completely. It's still going horizontally, but up and down, it stops going up, starts going down. If somebody says, what's the maximum height? Do not go play right away with the y equation. Play with the velocity in the y direction equation, because you know at the top the velocity in the y direction is 0. You can solve for the time that occurs at and then plug that back into the y equation to figure out what the y coordinate, what the height actually was then. Another thing I might ask you is what time does it hit the ground? Well, that's pretty straightforward. If something shoots off and hits the ground right here, the one thing you know about this spot is it's an x-intercept. It's hitting the x-axis. That means that y is 0. So that would be a big clue to you to go to your y equals equation and plug in 0 for y and solve for the time that occurs at. What if they ask you for the maximum range, how far it went horizontally? Well, If you just did what we just talked about and figure out the time it hits the ground with the y stuff, you could take that time and plug in your x equation to figure out what the distance is right here, okay? Now, for normal acceleration, these are handy little equations. If your acceleration is constant and it's just due to gravity, this is a good equation for your x's. This is a good equation for your v's. And you could replace the x's with y's also. It would be, because it's the same concept, but the acceleration would be replaced with the acceleration of the y and all that stuff. So you could use these, but you should be able to derive them from scratch. That's the whole point of this section right there. So brush up on your projectile motion, you'll be okay on that. And then the last thing, oh Lord, section 5.6, applications to engineering and physics. Oh boy, here we go. Lots of concepts in this, okay, and how to put them together. Look at the examples from your homework, look at the ones in the review assignment, look at the ones I did. Watch them, maybe watch the lecture again, because it is a lot of confusing concepts in here and I don't have time to go over them in the review. But essentially what's going on here is you have lots of different physical laws you need to understand. The first one is Newton's second law of motion, and that says force is mass times acceleration. So if you apply a force F on a mass M, it will accelerate. You'll probably use this one in two different contexts, okay? If they give you a force and a mass, you could use this to find acceleration. Acceleration, you can integrate and get velocity, you can integrate that into position, you can do all kinds of things with that. Secondly, though, weight is a force, and I'll get to that later on. But if you want to find somebody's weight, which is F, and you know its mass, you could multiply by the acceleration due to gravity. That's that 9.81 thingy or 32.2 thingy from the last thing to get the weight. But that's an equation later on. I'll harp on that. So force, mass, acceleration. It's all related by Newton's second law of motion. Okay, then what is work? Work is applying a force to an object through a distance, or you could take a little bit of force, just a little bit of weight, and move it a certain set distance, and you also did work. So it's about forces move through distances. There's two ways that could happen. You could have a constant big force. Force is 20 newtons. Somebody's pushing on something like this. And as you push on it, it moves a little bit, dx, 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 dx. This might be something you use in a spring. This might be something you would use if somebody's just pushing on a box. So dw is force times a little tiny change in distance. That's what work is. Work is force times a distance. On the other hand, if you have like a swimming pool and you're draining the water out, or you have one of those chains and you're lifting it up to the top, the question would be, same idea, but you're not lifting all of it at the same time. You're not lifting all the weight at the same time because they're moving different distances. So how do you handle that? Well, you'd use XDF. You take a slice of the chain or a slice of the swimming pool or wherever it happens to be. You would figure out the weight of just that little slice. That's what DF would be, okay? It's weight as a force. A little tiny slice of that. And X does not stand for literally X. X stands for how far you move it. It's a distance. So if you knew a little bit of weight and how far you moved it, X, you could do X times DF to get the work also. Now, it doesn't come up too much in this section, but how does it relate to energy? A little bit of work is exactly equal to a little bit of change in kinetic energy, which is negated of a negative change in potential. So that's how all the energy stuff works out. I don't think they ever ask you to do anything with energy per se, but just so you know, that's how they relate to work. Okay? Now with springs, there's something called Hooke's law, and it says F equals negative kx. All this means is if you had a spring and it was naturally some length, okay? So we're gonna call this 0 right now. X being 0 means that it's not stretched. And if I do take it and I stretch it out a certain distance, in this equation, X stands for the distance I stretch it from its normal equilibrium thing, okay? And so this relates how much force I pull on it to how much it will stretch. The force is F, X is how much it stretches by. The negative is there because the spring wants to kind of pull back on you. If you're pulling to the positive, there's a negative there because the spring pulls back in the negative and so on like that. In practice for Hooke's law and for anything with work, you could probably drop the signs. I'm not going to be too worried about it. In fact, when you get all said and done, if you do your whole problem and you get at a negative answer, just make it positive because they're asking how much work was done or how much energy is in the spring or something like that, how much work was done on the spring. Just make all the works positive no matter what the signs are, okay? Doesn't really matter. But you could use that to figure out the two. Now, the constant proportionality here is called K. It's your spring constant. That is a property of the material itself. Some springs are stretchier than others or tougher, thicker, things like that. So probably in most of these problems, the first thing they'll do is they'll tell you, okay, a force of blank newtons causes a spring to compress or stretch. It works for compression too, by 5 meters. Okay, well, you got a force and a distance, plug them in, solve for K. Okay, the first thing you're gonna do is probably solve for the spring constant so you can use it subsequently later on with things. And if they ask you how much work was done to stretch out the spring, well, what is work? Work is force times a little distance dx. You have an equation for F from Hooke's law. So you take negative kx, plug it in for F right here. You have negative kx dx. You integrate that from where you started stretching it to where you ended stretching it. You figure out the work done on the spring. Okay? So that's essentially all they'll do with the springs. Like I said, potential energy is negative work. Probably not going to come up, but if you're a physics kid, you might appreciate that. Momentum, little p. It is a measure of inertia, how hard it is to stop an object that's in motion. There are two factors that might influence how hard it is to stop something: how heavy it is and massive it is, m, and how fast it's coming at you, v. So momentum puts those ideas together and multiplies them to get the quantity that kind of represents something's inertia, mass times velocity. Okay, so momentum is mass times velocity. Well, let's see here. If you kind of rearrange that, if you took the derivative momentum equation with respect to time and relate to Newton's second law, it turns out that a little change in momentum, dp, is force applied for a little bit of time. That is known as an impulse, okay? If you add up all the little changes in momentum, you get a net change in momentum. You know, how much does it change by? You add up all the changes, the little dp's are little changes in momentum. You add them all up, you get the total change. That is known as an impulse. An impulse is the total change over some time of momentum due to a force applied for a time. Its letter is J. You don't need to know that if you don't want to. You can just call it delta P because that's what it is. It's a change in momentum. That's what it is. And how do you find that? Well, dp is f dt. So you integrate your force times dt, and from some starting time to some ending time, it's just some function given, and it will give you the change in the momentum. Change in the momentum, okay? So let's say the classic thing is the baseball guy. He throws a baseball at a batter. It's got some momentum. Let's say the momentum is 5. And then you apply a bat to it, and you apply a force for a certain amount of time. They give you an equation for the force. You could integrate f dt to get the impulse. And say a change in momentum is negative 20. Well, how do you find the new momentum after that? The momentum was 5. The impulse, the force applied for time, was negative 20. So if you had 5 and you change it by negative 20, what's that make it now? Negative 15. That means the new momentum is negative 15. That means it's going in the other direction. And you could go back to P equals mv to figure out what the velocity is, since the mass never changes. Okay, so impulses that are there is basically the integral of force with respect to time. Okay, now moving right along, mass. Okay, one thing you definitely want to get understood as you get forward with things, because a lot of things depend on mass, is how does mass relate to density? Okay, well, it depends on what kind of density you're talking about. In this unit, there's only 2 kinds you might need to worry about. This first one, dm, is rho dx, and this last one, which is rho v dv. Now, why? Well, if you go on to Calc 2 and 3 and in college like that, they'll do it over areas and stuff. It's the same concept. But essentially, what is this rho? This rho is a density, but it's got a little L in it. It's a linear density. So if you knew the mass of an entire length, okay, it has no width, it has no height, it's a one-dimensional thing, just a line. If you knew the mass of the whole thing and the length of it, you could come up with the mass density per unit length. That's what this rho L is. You could take the mass, divide it by the length. So the mass was 5 kilograms and the length was a meter. It'd be 5 kilograms per meter. That's what rho L would be. But what you're probably more traditionally comfortable with from chemistry and stuff like that is the normal thing that you grew up with, which is volume density, mass per volume. So if you took a little cube or something like that, what's the density of that? Well, that's what this rho v is. It's mass per volume. In either case, if this one over here is mass per length, and I multiply it by a little bit of length, dx, then I'm going to get a little bit of mass. On over here, if you've got a density per volume, rho v, and you multiply by a little bit of volume, you're also going to get a little bit of mass. So those are good to know. And you can go 2D on it as well. If you had a little bit of area and you knew the density per area, like kilograms per square meter, times a little bit of area, then you could find that'd be a little bit of mass too. So that's the relationship between density and mass, okay? Depends on what density you're talking about. If it's a linear density, multiplied by like a dx or a dy. If it's a volume density, multiplied by just dv. A dv would be something you have to set up with normal slicing and crap like that. Okay, then you got your center of mass and gravity. Once you can set up what dm is, all you got to do is plug in this equation to figure out the center of mass or gravity is for, say, x. Okay, so if you have x, the average x, this bar means the average x. Again, think of this as where on the x-axis you would have to put your finger to balance this figure, so it wouldn't there'd be just as much mass over here as over there, and that's why it's called the center of mass. But the bar on top means it's the average or the center of mass. If it's an x, it's the center of mass in the x direction. Well, okay, here's the equation for it. Just use it blindly. Integral of x dm over the integral of dm. Okay, and on the bottom, the integral of dm is just going to be m. It's going to be total mass. You're just adding up all the little masses, so you're going to get total mass. On the top, though, is where the letter really comes into play. If it's the average x, you'd put the integral of x dm over the integral of dm. If they asked you for average y, you'd put the integral of y dm over integral of dm. If you're going 3D in Calc 3 and then you want to find the average z coordinate, well, guess what you do? It's the integral of z dm over dm. So it just depends on what you're doing. Plug in the formula. Once you get dm, it's pretty much cake from that, okay? Like we said before, you got the acceleration to gravity. That's a special acceleration, little g. It is 9.81 meters per second squared in metric, or 9.8 if you want to use that, or 32.32 feet per second squared in English, or 32 if you want to use that. Why do you need that? Well, in this section with applications, that's how you get to work. Or, excuse me, not work. Weight. I'm even confused my own letters up. Weight. Weight is mass times little g. This is just F equals ma with new names. Weight is a force. Mass, g as an acceleration, okay? So this just tells you the force. It's a weight. Weight is a force. It's how much the earth pulls you down towards it. It's a force pulling on you, but that's what weight is. Weight is a force, and it's equal to mg. Now, of course, you can go infinitely small on this thing. A little bit of weight, dw, is g times a little bit of mass. If I just have a little bit of mass in this gravitational field g, it'll be a little bit of weight on this. You might even want to not write dw here. You might want to call it df as a reminder that weight is force. You could write dw equals g dm right here. You could write df equals g dm, whichever one makes sense to you. I use w because weight, but most of your equations involve this kind of stuff have df's in them, like xdf for work and stuff like that. So you might want to, instead of having a dw here, you might want to have a df, okay, just to keep it straight. This is a little bit of force. Just remember, weight is force, no difference. And then we talk about pressure, okay? Now pressure is like a force per area kind of density. So if I had an area, I don't care how thick it is, I don't give a dang about that. And there's a total force applied across it. If you could find the density of that, how much force is applied per little area, that's what pressure is, okay? And if you move things around, if P is F divided by A, then F is P times A. So the entire force on some kind of area is given by the pressure on it times that area. Well, if you go down really, really, really tiny, like a strip, like a little tiny piece of area, then a little bit of force on something due to pressure is equal to the pressure times a little bit of area. And it's probably going to be some kind of strip that you're going to take out like that. And then, of course, you got hydrostatic pressure. I don't think that'll even be on your test, honestly, but it is something to know as well. The farther you go down into a fluid, the more pressure there is from all the weight of the fluid above you pushing down on you, and it pushes in all directions. So this is an equation for the pressure that pushes on you at a certain depth, h, below the surface. H is height, but it's not, but height usually means like above something. No, not in this case. Height means how far down you are below the surface of this liquid or whatever you're dealing with. And the pressure is given by the density, volume density, okay, so kilograms per cubic meter kind of thing, times little g, which would be 9.81 meters per second squared, times your height or your depth below. And you might need that. There was a problem on one of the things, I think I modeled it, where there's a dam, and I want to know the total force on the wall of the dam and how much it could withstand and stuff like that. So what do you have to do? Well, you can figure out the pressure at any depth due to this. If you know the pressure acting on a strip like this with a certain area, you know, the pressure acting on that area. You could find a little bit of force against the wall, and then you add up all the strips from here to there, and you can see what the total amount of force is on this dam. So lot of concepts in the last couple sections. 5.5 projectile motion, and 5.6 very, very physicsy, very, very engineering, very difficult to put together if you haven't taken those courses, or especially since you're new, applying it to calculus is difficult in itself too. So those are all the concepts that might be on your test. And like I said, that kind of concludes everything. You have your first review assignment out of the book due on Thursday. You have your second review assignment, which will be posted. They'll be due on Friday. And once those are done, you will have your take-home test to worry about. You can worry about that over the weekend, get it done at your convenience, take 10 hours on it. I don't care. Just be ethical. Don't be cheating with other people. Don't be posting on like a forum, say, how do I do this? Can you do this for me? Something like that. Don't do that. Do your best. I will take good care of you. I will be lenient, especially on the hard ones with the physics ones. I'll be pretty lenient on that. And whenever you have extra credit stored up, you can use in case that goes awry too. So you'll be all right. Just do your review assignments, study, take your tests seriously like you always do, and we'll be okay. And then, like I said, after that, we're just going to dabble in some other ideas. They are important. Just because there's not an entire unit dedicated to them or an entire month I'm spending on them does not mean they're not important. They're just things that we didn't get time to get to. And if you take Calc 2 or you go on to Calc 3, you can guarantee everything I'm going to touch on after this test will still be coming up far more in depth. So you want to know the basics of those, and that'll be that. So guys, that's all there kind of is to it. Good luck on this. If you got any questions, that's what the help sessions are for, and I will be talking to you guys soon. Have a good day.